So this is our Math 20-2 lesson for Wednesday, December 2nd. Because the internet is down, when it's ready I'll be posting, or when I can, I'll be posting the link into Moodle for this class. So today we are going to look at similar objects and specifically scale models and scale diagrams. So rather than talking about two-dimensional objects and diagrams, we're now going to be looking at three-dimensional objects. So let's get started. So our key ideas are that we have two similar objects when the objects have proportional dimensions. So similar objects have dimensions that are proportional, which means that if I have a block like so, my beautiful block, and it has a side length of s, if I have another block and it's proportional, that means that whatever scale constant I use, that each of my sides are going to have that same scale constant to multiply to it. So let's think of something other than SS, side, side, side. Let's look at something like a rectangular box. So this is the length, the width, and the height. And my similar object would have k times the length, k times the width, and k times the height. And that's how I could know that they're similar objects if all three dimensions have the same k scale factor applied to it. The scale factor is the ratio of the linear measurement. So it's not the area or the volume, it's a linear measurement of an object to the corresponding linear measurement in the similar object. And so that's why we're dealing with the length, and it has to be k times the length, and the width, and k times the width, and the height, and k times the height. So it has to be corresponding measurements. And we use those measurements in the same units. If we're in the process of creating a scale model or diagram, we determine appropriate scale that we're going to use based on the dimension of the original object and the size of the model or diagram. So you choose your scale not just randomly, but you look at, okay, I have a paper that's this size, so I need to know what my scale is that's going to fit it onto the page, or fit it so that that model is going to be small enough or big enough, etc. So let's talk about how we do these things now. Oh, let me scroll up to the top. So as we've been doing, we can multiply any linear measurement of an object by the scale factor, and that calculates the corresponding measurement of the similar object. And as before, we can find k, the scale factor, by taking the linear measurement of the scale model by the corresponding linear measurement of the object. And so if we think of this as always having the reproduction over the original. And so really we're looking at what are we starting with and what are we producing out. And so the reproduction is always what goes on top. When a scale factor is between 0 and 1, the new object is a reduction. When the scale factor is greater than 1, the new object is an enlargement. And that's something that we've been working with previously. So now let's look at some examples. We are going to determine if these objects are similar. So Sandeep is a chef, and in his restaurant he uses frying pans of various sizes. We're being asked if his frying pans are similar. And so to be able to determine if they're similar, we would have to determine that each of the dimensions has a similar scale factor attached to it. And so we look at the diameter to start with. So what is the scale factor as we go from the small diameter to the large? So K, let's treat the large as the reproduction, that's 30 centimeters, and the smaller diameter is 20 centimeters, and so we have a scale factor of 3/2. Now we compare our depth, because remember that all of our dimensions have to have the same scale factor attached to it. So in the relationship between the scale factor between the depth of the large over the depth of the small, we have 6/2 or 6/4, and that reduces down to 3/2. So we're not quite finished. We have to make sure it's the same for the length of the handle. And again, we test to see if our scale factor is the same for the handle. We have 24 centimeters over 16 centimeters, and 24 and 16 have a common factor of 8. I divide top and bottom by 8, and again I get 3/2. And so because all three dimensions have the same scale factor, we can say that the frying pans are similar. So Sandeep's frying pans are similar. Let's look, let's finish that. Sandeep's frying pan are similar because all three dimensions have the same scale factor. And that should be a C, scale factor of 3/2. Let's now go to example number 2. So Esmeralda bought this toy tractor to give to her younger brother for his birthday. The dimensions of the toy are given in the diagram to the right, and the scale factor on the package is 1/16. She knows that her brother will want to know the size of the real tractor, and she wants to know how she can go about calculating this. So remember that our scale factor is the reproduction, in this case the toy model, over the tractor itself. And so we're told that our scale factor is 1/16, so that's 1/16. And we know that the scale factor, it's a reduction from the actual tractor down to the model, so it's 1/16. And we're putting the measurement of the model on top. And so we're looking at the height, which is 12.7 centimeters, and I'll call that H for the tractor. So to solve this, we will take and multiply, do cross multiplication. So we have 1 times H, which gives us H, and we have 16 times 12, and I'm just going to do that on the calculator here. 16 times 12.7, and that gives me 203.2. So we have 203.2 centimeters, and we might choose to convert that into meters. So if I take this and multiply it by 1 meter per 100 centimeters, my unit of centimeters cancels, and I take 103.2 times 1 divided by 100, and that gives me 2.03 meters. So the height of the actual tractor is 2.03 meters. Now we are going to look at the width. So again, we have our scale factor. which is 1 over 16, and that's equal to the width of the toy, 9.5 centimeters, divided by the width of the actual tractor. And again, we solve this by cross multiplying. And so we have W times 1, which gives us W, and 16 times 9.5, and that gives us 152 centimeters. Again, I can convert this to meters by multiplying by 1 meter over 100 centimeters, and the width of the actual tractor is 1.5 meters, and I'm rounding this to the nearest tenth. So we have 1.5 meters. So we have the height and the width. Now all we need to find is the length. Sorry, so let me just start again for the length. Again, it's 1 over 16, our scale factor, times the length on the model, which is 19.1 centimeters, over the length on the tractor. We cross multiply, and the length is 16 times 19.1, and we get 305.6 centimeters. We multiply this by 1 meter per 100 centimeters, and that gives us 3.06, rounding to, and that's to 2 decimal places, so I'm going to actually round that to 1 decimal place to the nearest tenth, and that would be 3.1 meters. So we can say that the dimensions, sorry, that should be an I, the dimensions of the tractor are 3 meters long by 1.5 meters wide. Let me just clean that up. And 2 meters tall. Okay. And as I look at this, I should go 3.1 meters and 2.0 so that I'm consistent about being to 1 decimal place. Let's look at example number 3. Nadia has found plans for a bookend in the workshop, in a woodworking magazine. The plan includes a scale diagram with a ratio of 1 to 5. So the scale from the actual to the diagram is 1 to 5. And we have the measurements of the object, the bookends, in the diagram. Okay, so our diagram is 1 3/4 inches tall. So how tall would the bookend be? Our side view is 1.5 inches wide. What would be the actual width? And so on. Okay. So let's start. We have 1 over 5, and that's equal to the diagram over the actual object. So let's start with the base width. And so we have 1/5, and our diagram is 1.5 inches to the actual base width. So I'll call that B. So B is equal to, again, we cross multiply, and we have 5 times 1.5. When we calculate that, we are going to get 5, 7, well, let's actually calculate it out. So this would be, turn that fraction into a decimal. So that's 1.5. So we have 5 times 1.5, and that will give us 7.5 centimeters. So the base and I'm calling that the width as would be 7.5. Let's do the thickness, the base thickness. And I'll call that T. So again, 1/5 is equal to the base thickness, which is 1/4. So 1/4 inch over T. And so T is equal to 5 times 1/4, which gives us 1.25, and that would be in inches. Let me just correct myself. I wrote centimeters here, but it's going to be in inches. So we have our base width, our base thickness. Let's go with the length of the hole, or the front surface. We'll call that the length. So our actual length of our bookend, and it's 1 inch. So we have the length, sorry, just need to clean that up, just give me 1 second. We're calculating the length. Again, we take our scale factor of 1 to 5. The diagram is 1 inch, and so our length is going to be 5 inches. Right? And then we have the height of the back. Or we could just do, maybe let's just do the overall height, which is 2 inches. And so when we calculate this by cross multiplying, we have a height of 5 times 2, so it's 10 inches tall. So we have our dimensions. The base width is 7.5, the base thickness is 1.25, the length at the front is 5 inches, and our height is 10 inches. Let's do one last example. And this example has us looking at creating a drawing, and we want to draw a pipe. So each pipe has an inner diameter of 1.5 meters with a wall thickness of 0.18 meters and a length of 2.5 meters. And she wants to do a scale drawing of this. And so it's important that we know what size of paper we're going to be working with. And so let's imagine that we're just working on letter paper, and so we have in millimeters 215 our millimeters are of the page. It's 215.9 by 279.4. And this is a regular 8.5 by 11 page, but in millimeters. Okay, so I'll just take that paper size sheet out. I just picked it up off the internet so that we could have that information. And now let's decide what's the best scale factor for us. So the first thing we need to do is think about how we're going to draw this. And if we try to draw something with perspective, so where you're going off and meeting a point at the end, so you're showing that often skews your actual measurements, and so very often we don't do scale or perspective scale drawings with perspective, because the intention of the scale drawing is to not distort our measurements at all. So what we're going to draw is an example of, or if we look down at this from the top, think about looking at a can without perspective. Really all we have is a rectangle. So we'll have a rectangle which would be, so the inner diameter would, from here to here, would be 1.5 meters, and we have 0.8 and 0.8 meters on each, or 1.8 and 1.8 on each side. So our total width is 2 times 0.18 plus 1.5. So let's just determine that. 1.8 times 2 plus, oh, helps, I've got to turn the calculator on, so 0.18 times 2 plus 1.5 . And that gives us a total width of 1.86 meters, and our length is 2.5 meters long. The other face, so this would be the top view, and the other view we want to do is this one. And so we know that this also is 1.86 meters wide. Now we have to think about our page and how that would best fit on our page. So if I think about splitting that page in half, I can have my top view and my front. And so the question is, can I fit the 2.5, which is better, to put the 2.5 like this and the 1.86 meters this way, because essentially I have 1.86 meters twice when I do that top view like that. So I want to see what scale is going to be best. I know that my page is 215.1 millimeters, so K is equal to the drawing over the actual, and our actual is 2. If we're going to put the 2.5 this way, we have to turn that into millimeters, and we know that there are 1,000 millimeters in a meter. So I'm multiplying 2.5 by 1,000, and that gives me 2,500 millimeters. So I put that over top this way, 2,500 millimeters to get K. And the other thing that we have to pay attention to is our height of the page. Test to see which value would work, what K value would work there. Now, I know we need to use the same one, but we don't want to pick a K value for one dimension and then find it doesn't work the other way. And so we're going to take and add those two together. So 1.86 times 2. And just to make sure I don't make a silly mistake, I'm going to do it on the calculator. So that's 3.2 meters. And we have 3.2 meters times 1,000 millimeters per meter. And so we're going to put on our denominator 3,720 millimeters. That's our actual, and our drawing, our paper size is 279.4 millimeters. So now we're going to divide these out, and between the two of them we'll pick a scale factor that works and then round it to a fairly nice value. So we take 215.9 divided by 2,500, and that gives us 0.08636. And if I turn that into a fraction, I'm just going to check and see what it will give me as a fraction, and it doesn't come out to a nice fraction, so we'll just leave it as a decimal for now. And then we do the 279.4 divided by 3,720. Oops, I need to do that again. Missed the 20. There we go. And we have 0.75108 approximately. And now we have to decide which one will work. Well, if I choose the larger scale factor, when I multiply that my height, this value, by that larger scale factor, let's just do that, 0.8636 times 3,720 millimeters, what we'll find is it's too large. So 0.08636 times 3,720, and our page isn't big enough, right? Our page is only 279 millimeters. So we have to choose the smaller one, and we want to make sure that we have enough boundary around it. And so what I'm going to choose as a scale factor is 7. Sorry, and I should have another 0 here. So if I put 75 over 1,000 and reduce that down, let me just put 0.075, turn it into a fraction, see what I get. And that gives me 3 over 40. That's kind of an awkward number, but that's not too bad. So we'll use that as our scale factor, 3 over 40. So I'm just going to skip to a new page and we'll do our calculations. So imagine my page. I have my top view, or the top view and the side view are identical, and we want this to be 2.50 meters and 1.86 meters, like so. And let's calculate the length. So we take K, so the length on the drawing times the length times the actual. So our length on our drawing is going to equal to 3 over 40 times 2.50 meters. And so our drawing is equal to 0.1875 meters. Again, we convert that into centimeters by taking 0.1875 meters times 100 centimeters per meter. And so it's 18 centimeters, 18.75 centimeters, which is slightly narrower than our page. Then we take and find the height of the diagram, and that's 3 over 40 times 1.86 meters. We do exactly the same, calculate it exactly the same way. And we get a height of 0.1395 multiplied by 100 to give us 13.95 centimeters in height. Then we do our front view. We have our width, so this is 1.86. We already know how wide that has to be, 13.95 centimeters. And then we have our inner, which is 1.5. So this is 1.5 meters. And so we find the inner diameter by 3 over 5 times 1.5 meters on our drawing. So 3 times 1.5 divided by 40. And we get a diameter of 0.1125 meters, which is 11.25 centimeters. And so it fits inside of our page. Our page this way is 200 and, let me just pop back there, 216 approximately. So 216 millimeters, which is 21.6 centimeters. And so we can see that our width is small enough. And if we check the height of this way, it's about 280 millimeters, which is 28 centimeters. And we know that we have two heights of 14 centimeters, and so that's going to be pretty close in terms of the actual height on the page, but it will fit. Okay, so we've chosen a scale factor of 3 over 15, and we made sure that it would fit. I encourage you to do some practicing. Oops. Let's practice. There's your page numbers for practicing, and hopefully Moodle will be up and working tomorrow, and we will have a class. We'll talk to you soon. Bye now.